Greetings! Today we're talking about our simplified pi over 2 BPSK decoder, working under the assumption that symbol timing and phase have already been resolved to a single sample per symbol. This work fits into the much larger picture of acquiring phase, timing of symbols, demodulation, decoding, and correlation to the fixed patterns of the start of frame field in the physical layer header that helps define each DVB-S2 frame. The DVB-S2 physical layer header is sent using a modulation scheme called pi over 2 BPSK. This scheme is defined in the standard. Since we're using GNU Radio as a reference design, we decided to make a custom block in GNU Radio to do this. This block will evolve to include our specific type of correlation for the starter frame as well. Given that we needed a block, we had to learn how to make one. There is a very useful GNU Radio block coding style guide located here. The link is in the show notes. There is a helpful set of guided tutorials on the GNU Radio website here at this link. A block in GNU Radio is the unit of signal processing from which you build a flow graph. It can implement a very simple function or it can be very complex, and it might or might not take parameters that control how it works. Related blocks are grouped together into a module. The name of the module shows up in GNU Radio Companion as the category header for blocks that belong to the module. To help build blocks and modules, there's a tool built into GNU Radio called gr-mod tool. One of its functions is that it sets up a module. Another function lets you add blocks to that module. Using gr-mod tool is relatively easy. It sets up the right directory structure for you, and it provides templates in either Python or C++ for the implementation of your block. I'm not going to duplicate the tutorial here. Find this specific tutorial at the link in the notes. If you walk through this tutorial, you will be well on your way to being able to code GNU Radio blocks. After doing the tutorial a couple of times, we attack the problem of demodulating pi over 2 BPSK. We started with the definition in the spec. If we think of I and Q as coordinates in a Cartesian plane, we have what's called a constellation diagram. Using this visualization, in pi over 2 BPSK, the information is encoded as the direction of rotation around the unit circle. Clockwise 90 degrees, or pi over 2 radians, for a 1, or counterclockwise by the same amount for a 0, with each received symbol. Because the next stage of the received pipeline is a correlator, we chose to output positive 1.0 for a clockwise rotation and negative 1.0 for a counterclockwise rotation. This encoding will be helpful later when we change to a more sophisticated demodulator implementation. The signal never stays in the same quadrant for two symbols, nor does it ever cross through the center by moving 180 degrees at once. If we see either sequence in the received symbol stream, we know it is an error. We pass that information along to the next stage as what's called an erasure, encoded as a value of 0.0. This really needs to be reviewed to make sure we have interpreted it all correctly. Code for this block can be found at the following repository and discussed in the code review channel in Slack. Once we thought we understood the way pi over 2 BPSK worked, we wrote quality assurance test code. The gr-mod tool sets up unit testing templates for you so that you can test first like highly evolved and successful programmers always do. Then we wrote some demodulation code. It didn't work. We wrote more. It didn't work either. QA tests kept failing. We went back to the drawing board and realized that it would never work. We proved that the problem couldn't be simplified combinatorially. We then wrote a table lookup for the combinations of previous and current symbols. Here's the table we started with and went back to. Because we assume the symbols are already synchronized and lined up for us, we only need to pay attention to the sign bit of each sample, whether it's positive or negative. We receive a series of complex signal snapshots. We establish a history where we tell GNU Radio that we need to keep track of the most recently received complex signal along with the current one. This means we use the setHistory function in the constructor. The history value is 2. We need the previous signal in order to tell which direction the signal moved and whether or not that move was valid. We compare the previous signal to the current one. In our complex signal world, the previous result and the current result are each composed of a real and imaginary part, representing the in phase or I and quadrature or Q components of the signal. Each part is a float. The lookup is achieved by taking the signs of previous I, previous Q, current I, current Q, with the sign bit macro, and converting those sign bit results into an integer by multiplying each one by place values 8, 4, 2, and 1. This std : sign bit macro returns 0 for positive value and non-zero for negative values. So, we use an old C programmer's trick to convert it into Boolean 0 or 1 by negating it twice. This trick is called the double bang. The output is a table lookup. Mega is a list of floats constructed as follows. The index created by the integer value Tesla, which is a binary coded number derived from the sign bits of the previous and current complex samples, will give the correct output value that corresponds to that combination of previous and current complex signal inputs. A GNU Radio block is given a certain number of samples to work on each time its work function is called. That's no problem for operations that look at just one sample at a time, but we need to look at both the current sample and one previous sample. So how do we ever manage to handle the first sample that's passed into the work function? Well, GNU Radio has a solution for this called history, and we call the set_history function and tell it the number of adjacent samples we need to examine, in this case 2. GNU Radio then arranges that each work buffer contains the extra previous sample that we need in addition to all the new samples. Once we've figured that out and got the table indexing right, the simple unit test case we'd constructed finally passed. Assuming that the demodulation is correct, the next step from here is to take our starter frame and look for receive patterns that match it. When this happens, we will produce a tag. Tags in GNU Radio are synchronized chunks of information that are attached to samples. It is like metadata that can be used by other blocks. For this block, we are going to follow the conventions in the general correlation estimation block. This means that there will be several tags that can be used by downstream blocks that need them. Those downstream blocks have already implemented functions that consume the tags, so if we produce them, it makes for more useful flow graphs.
Black cat on the roof tonight.